Problem number 12. We're giving a long list of properties that three different vector fields satisfy, F1, F2, F3, F4. And each of these vector fields is defined on all of all of R2, except for the origin 0, 0. Our question is, does this convince us that each of these vector fields is conservative, or might the vector field not necessarily be conservative? Okay, so the first one, we're given an explicit formula here for F1, negative y comma x here. Let's check cross-partial derivatives here. The cross-partial derivatives, we'd have to have partial p, partial y equal to partial q, partial x. And in fact here, this actually is false. Partial p, partial y is -1, partial q, partial x is +1. Those aren't equal. So not only is it not necessarily conservative, it's not conservative. The second one is F2 is path independent. The line integral along any curve C of F2.dr is independent of path. This is F2 is conservative. This is one of the things that is equivalent to a vector field being conservative, is the path independence property that the line integral over this curve of F2 is equal to the line integral over this curve of F2 is equal to the line integral over this curve of F2. Okay, so not conservative is definitely conservative. For part 3, we're given that F3 is equal to PQ. Those are just components there. And on the domain D, everywhere except for the origin, we have partial p, partial y is equal to partial q, partial x. And so as it turns out, F3 is not necessarily conservative. Now, this is a necessary condition for our vector field to be conservative, but here, this is an example where our domain is not a simply connected region. It's all of R2 except for the origin. So there's a hole in the middle of our domain here, and that makes it not simply connected. Go back in class, there is a vortex field. There's a vortex field that we covered in our class notes, for which you had this equality of cross-partial derivatives, but it happened to be not conservative. So this is not necessarily conservative. And then finally, F4 has the property that for the unit circle, C1, so let's draw some axes right here. Here's our unit circle. The line integral around C1 is equal to 0. F4 is not necessarily conservative. So this one here, it's not necessarily conservative. Why is that? We're not told that the line integral around every closed loop is 0. It may happen that just by dumb luck that the line integral around this closed loop is 0, but it doesn't say for this closed loop or this closed loop or this closed loop or any closed loop that we come up with. We're only told this for one particular closed loop. So how might we change these? How might we change the ones that aren't conservative to become conservative? Well, for this one, we'd have to, if we were to patch this one up by changing that to like plus y, then this would end up being conservative. You can find a potential function. I think f is equal to xy would be a potential function for this f1. So the problem is asking you how to change these to make these conservative. I'm just kind of tacking them on here. This one's already conservative. For this one, we'd have to change it so that the domain is simply connected. So if this were over at all of R2, the region that's all of R2 is simply connected. There's no holes in it. And so that would make that would be enough here to say that F3 would be necessarily conservative. And then for this one, we'd have to change it to say for every loop, every closed loop in the plane, the circulation around it is 0. Okay, that is problem number 12. Let's take a look at problem number 13. We're asked to parameterize these two surfaces here. First one, the portion of the sphere, x squared plus y squared plus z squared is equal to 4. Y and z are both non-negative. So the way that we're going to do it, we were asked to use u and v here. So usually I would do this with phi and theta, but we can do it with u and v. So 2 cosine u sine v, 2 sine u sine v, and 2 cosine v. It just is good to know that, I mean, usually we would do this with cosine theta sine phi, sine theta sine phi, and cosine phi here, along with the radius of our sphere 2 out in front. This is a good one to know just off the top of your head. What are the bounds of the parametrization? Well, so u is corresponding to theta, and v is corresponding to phi here. And so usually phi would be running from 0 to pi. However, the z is non-negative part of there will restrict phi to be between 0 and pi over 2. So that makes v between 0 and pi over 2. As for u, which is playing the role of theta here, in the xy plane, we have y is non-negative here. We can see theta is running from 0 to pi, so we'll make u run from 0 to pi there. And then the last part here, part of the graph, x is equal to 1 minus z squared, where x is greater than or equal to 0, y is between negative 2 and positive 2. R of uv here. Okay, how are we going to do this? X is written in terms of z, so I'm going to set z is equal to u, and so then x will be 1 minus u squared. Meanwhile, y is free, y can be anything, so oops, I don't want to write y there, I'm going to write v here. So what are our bounds on u and v? Well, y is between minus 2 and 2, v is between minus 2 and 2, and if x is greater than or equal to 0, we want 1 minus u squared to be greater than or equal to 0. This is true when u is between minus 1 and positive 1. So these are my solutions here. You may have come up with other solutions that in general parameterizations are not unique. For example, if you swapped u and v here, that would certainly be fine. But this is a set of correct answers.